All right, so I'll go through, I want to do two problems from 2-4. If I can find my pen, there it is. Okay, so here was one I thought was a pretty hard homework problem from 2.4. This guy, okay, chain rule stuff. It's a good problem. You got to really think about it a little bit though. Assume f and g are differentiable functions, and h of x is defined as f of g of x. So it's a composition of the two. Okay, so here's the part that I want to make sure we all understand. Suppose the equation of the line tangent to the graph of g, so that's the inside function, at the point 1, 9 is this, y equals 4x plus 5. So all that is, at the point 1, 9, that's the equation of the tangent to the curve. What's the curve? We have no idea. They don't tell us, right? They just tell us that it's some random function g of x and some random function f of x combined to form h of x, but we have no idea what those are. So it could be something like this. It might be that the function sweeps in and does something like that, maybe, right? Can't go vertical, but you get the idea. So that's the tangent to the curve. That's all we know, though. We know that the point of tangency is at 1, 9. And what else do we know about that tangent line?
Slope.
What's the slope? 4. Yeah, so we know the slope of the curve at this point is 4, right? Okay, so we know also then they give us this other curve. They tell us that the equation of the line tangent to the graph of f at the point 9, 5 is 3x minus 22. So similarly, we know down here that this is just a point of tangency. We don't know what the graph is doing, but maybe it's doing something like, that's pretty bad. You get the idea, something like that, right? Oh, okay. So next period, you mean?
Yeah.
Oh, that's fine.
You just told me to check it.
Okay, thank you. So and we know that the slope of this line is going to be 3, right? Because the tangent line to the curve there is 3. Okay, so. All right, so what does the chain rule tell us? We don't know what the functions are, but we know that h of x is defined as f of g of x. So if I'm going to differentiate this thing, what would the chain rule tell me I'd have to do? So u being, we're calling u g of x, right? So h prime of x would be f prime of g of x, which we could call, and we have called u, right? Times the derivative of the inside function, which is g prime of x. Look what the question is asking us to do. It wants us to calculate a couple things. It wants us to calculate h of 1, so the value of the composition function h when x is 1, and it wants us to calculate h prime of 1, so the slope of h when x is 1. And then using those to come up with the equation of a tangent line is just pre-algebra stuff, algebra 1 stuff, right? That's no big deal. The calculus comes from part A, though, okay? So how are we going to do that? If we want to evaluate this at 1, what should that be? Well, that's giving us h prime of 1 is going to be f prime of g of 1. Do you see that? Okay, that's really important. Okay, so the input of the function f is the output of the inside function, right? G of x. That makes sense? So we're evaluating g of x at 1, and it's outputting some value, which then becomes the input for f. Okay? You do that all the time without really thinking so hard about it. You do that all the time when you do things like, let me just leave this for just a moment. Like if we were to do something like, for example, we're going to do the f of x equals, I don't know, let's just say it's the square root of x plus, make it easy, x plus 3, right? The inside function is x plus 3, and the outside function is the square root of x, right? So if I'm evaluating this, let's just say we're plugging 6 in. Really what we've got here is the square root of hand, and hand is the output of x plus 3. You don't really think about it that hard. You're just going to use order of operations when you simplify this thing. That really is a composition of functions, right? X plus 3 is giving us an output of 9 when x equals 6. And so the 9 is what's going into the square root. So f of x equals the square root of that 9, which is 3. Like I say, it's not a big deal. You do it all the time. It's very familiar. But here it's a little stranger because we don't have the functions. Okay, so then we've got h prime of 1 is going to be f prime of g of 1 times g of 1. Well, this is the function g right here, isn't it? I should probably write that. Yeah. Oh, it should be g prime, sorry, g prime. You're right, g prime, my mistake. G prime 1. So this is the function g. We graph that one first. The graph of g is given here. It's got a point of tangency of 1, 9, and the slope of the tangent line is 4. Right, so we'll just call this g of x. So what is g prime of 1? 4. Everybody see that? Because the derivative, this tells us if this is g, right?
Yeah.
At the point x equals 1, y equals 9, the slope of the tangent to g is 4. And we know that because it's right there. Right, that's the tangent to g at that point. Okay? So we can replace, this guy gets replaced. There it is. I lost this a while ago. There. Okay. So this gets replaced with 4. Right? So what about f prime of g of 1? Well, what is g of 1? This is the function g. It's 9, right? When we input 1, we output 9. So g of 1 is 9. This was the graph of f, right? Would you agree? So what's the output of f when x is 9? Okay, what's the slope of the tangent? So in other words, f prime, doesn't this tell us right here that f prime of 9 equals 3, right? Everybody agree? Well, there's f prime of 9. So what is that? 3. Okay, so h prime of 1 in this case is equal to what? 12. Everybody get that? It's kind of tricky, huh? Okay. Questions on that? Let me pause. That's a lot of stuff. How I got the 3, sure. So we're evaluating f prime at g of 1. So first thing we have to know is we have to know what is that? What's the output of g when x is 1? So we look at our function g, right? Which is right. It's telling us this right here, right? The tangent to the graph of g is that at that point. So that's really telling us right there that the output of g at 1 is 9. Okay? So let me make an arrow. That's going, this 9 connects to that, okay? And then we want to know what's f prime evaluated at that place. Well, it's right here. There's f prime, isn't it? That's the derivative of f at 9 is 3. Yeah, because look. No, this is
Tangent to the line F.
tangent to the line. So if this is the green stuff, right? The line tangent to the graph of F at the point 9,5 is this line. Well, we don't really care about the y-intercept of that line. All we really care about is that. That's telling us the slope of the graph at 9, right? So this is telling us right here that f prime of 9 equals 3. Just kind of coded information there, right? And so f prime of 9 is 3. That's the output of the first link in the chain. The second link we decided was a 4. 3 times 4 is 12. Okay, so we know h prime of 1 is 12. What about h of 1? That's easier. We don't even need any calculus for that.
No.
Right? H of 1 is just f of g of 1. What was g of 1? Well, that was 9, right? We already knew that.
Wait. I have 9 on here. Okay. So when f of prime has the g of 1 inside of it,
Mhm.
what does the 9 have to do with the 3?
Because g of 1, f prime of g of 1 has 2 layers to it, right? We're taking the derivative of hand, but what's hand? Hand is the value of g at 1. The inside function is g. We don't know what g is, but we do know that g of 1 is equal to 9,
It's 9.
right?
Okay.
So g of 1 equals 9. F prime of 9, we know that that's equal to 3. Because when x equals 9, the derivative is 3. Okay? So that's how we're getting this. Now up here, we don't need the calculus. Up here, we're just saying g of 1. Well, g of 1 we already know from up here. G of 1 is 9, right? That's what that's telling us. G of 1 is 9. So f of 9, that's all we need to know, right? Let me scoot down a little bit. So h,
So it's not that g of 1 and f prime have anything to do with either as functions, but as numbers?
It's because the original points, 1, the 9. the
Yeah, I know,
9,
but
5.
it's the number, it's not the functions themselves.
it's the value of the function at a specific point.
Okay, but
We don't know what the function is, so we actually couldn't calculate. I mean, we just have to take it on faith that because they gave us these ordered pairs, we don't know what g of x is, but whatever it is, the value of g of x at 1 is 9. We don't know what f of x is, but the value of f at 9 is 5. Yep.
So if you were given a different, if the y value for the first equation was different than the x value for the second, you wouldn't be able to do this problem.
Exactly. You wouldn't. The only way this works is because, I mean, they're chosen pretty carefully. But it wouldn't work if the output of this function weren't the input of this one. You couldn't do anything with it because you don't know what the functions are, right? Okay? So then we decided here that this is 9, right? So then all we have to do is just evaluate f at 9, and we can do that. What is the value of f at 9? 5, right? It's right there. And we can see that, if we look up here, we can see that in this ordered pair. This is telling us right here that f of 9 equals 5. That's what that ordered pair is telling us. Right? And the rest of it, I mean, do we want to do the rest of it if we know what the point of tangency is, right? When x is 1, y is 5, right? So we get the point 1, 5. And we know that h prime of 1 we calculated to be 12, so that's the slope of the tangent line.
Right, so in order to find that, we have to multiply, wait, why do we have to multiply the second thing, the g prime?
We're not multiplying.
Wait,
We're evaluating f at g of 1, which is equal to 9. So f of 9 is 5. When we input into the function f9, it outputs 5 because of that point right there. That's our point of tangency. We know that's a point on F.
Why do we do the chain rule on that one, but not?
You don't. You don't use the chain rule on this one at all. This is not calculus.
No, not on the, okay, so why did we use the chain rule on the other one?
Because
but
it's a
not-
derivative. Because when we differentiate a function of a function, if there's two layers of the function, we have to have the chain rule. That's how we differentiate compositions,
Okay.
right? I heard the lights just went on there.
No,
No, like the opposite,
The
actually.
light bulb exploded.
Yeah.
Okay? And then, so all we'd have to do here, this is no, I mean, this is, really, this is pretty trivial now. If that's our point of tangency, we just get y minus 5 equals m, which is 12, times x minus 1. There's our line, right? Okay. Yep.
How'd you get to 4 and then times 1?
Because of, right there, because it tells us, let's go up to the problem, because of that, right? Let me draw a line to that. You got it?
Yeah.
Okay. Okay. All right. Here's the other one. Were we good on that one?
Yeah.
Okay. Now I'm recording this. I know I'm behind on my recordings. I caught up yesterday. Not on the notes, but on the recordings. So here's the other one I wanted to look at was this guy. Not really a super hard problem, but I want to just review the principles here. We haven't talked about this in a little bit. This is the last problem on practice 4, 2.4 practice 4. So if they're giving us a position function, right? Remember, this is the stuff we talked about walking at the front of the room. Real quickly, what's the relationship? If we have a position function, position as a function of time, if we're on a line at the front of the room, then if we say that this is 0, and that's the positive direction, then this is a position of positive 1, that's positive 2, this would be negative 1, right? Because it's a vector, so there is a direction associated with it. There's a positive position and a negative position compared to our reference point, right? So how is velocity related to position then? Derivative. Okay, how is acceleration related to velocity? Derivative. Okay, you get the idea? So then if we know the position function, we should write it like that because it's a function of t. If s of t is equal to the square root of 1 plus 6t, then that tells us that v of t is just s prime of t, right? So what would that be? So we got a 1/2 power on the outside, right? The square root's of 1/2 power, so we gotta do this in layers. So the square root of hand is just 1/2 times the square root of hand. Everybody agree?
Yeah.
1/2 hand to the minus 1/2. Okay, what's the next link gonna be?
6.
Yeah, so times 6. I'll just put the 6 on top. How about? And we can. So that would reduce to the 6/2 reduces to 1 plus 6t. Okay, so there's the velocity function. And then the acceleration function would just be the derivative of that. So it might be convenient for us to write this as 3 times 1 plus 6t to the minus 1/2 because it's on the bottom, right? And so a of t then, bring that down and get negative 3/2 times hand to the,
Negative 3 halves.
right, you gotta subtract 1. Times,
1 plus 6
no,
6.
6, there we go. So then the 6 and the 2 would cancel, I'm gonna end up with a negative 9 times 1 plus 6t to the minus 3/2, so let's just put that on the bottom. So the positive 3/2, either way. So there's a of t, there's v of t, there's s of t. All they wanna know is if position is in meters and t is in seconds, what's the velocity and what's the acceleration when t is 4? So we're just evaluating these functions at 4, no big deal, right? So v of 4. And really, would I even have to, like, these were easy to simplify. But it always pays to read the question first in calculus, because you can save yourself a lot of unnecessary work. What if this was a horrendous derivative that would have been very hard to simplify? And the whole purpose of this was just to find specific values of velocity or acceleration. Would I have wanted to simplify that algebraically? No way, because all I'm gonna do is plug in numbers, and numbers are easy to simplify, right? See the strategy there? So V of 4 would just be 3 divided by square root of 1 plus 24 squared root of 25. What do you know? Positive 3/5. What would the units be? Everybody see that? Because if we're differentiating, it's easier to see if you think of it like this. V equals ds t, right? Instead of s prime. Then if we write it this way, we know we've got units of, we're looking at change in position over a change in time. So we've got units of meters over units of seconds, right? So we end up with meters per second. And acceleration, we plug in, we're going to get -9 over 1 plus 6 times 4, so that's 25 to the 3/2. Yeah, can I do that? Good, so you're gonna do the bottom first, the 1/2 power is the square root, so get the square root of 25 is 5, cubed is 125, okay? So -9 over 125, and I will just leave it at that, so that's, what are the units gonna be there? So we know acceleration would be, there's two ways we can think about this. This is gonna be, we could think of it as being v prime of t, but we could also think of it as being dv dt, right? So if you wanna get the units right, like I say, this is an easy way to think about it. So velocity would have units of meters per second divided by time is in seconds. So you get meters per second, right? But what do we do in physics with that? Meters per second squared, just multiply by the reciprocal, right? Okay? All right, very good. Okay, so that's kind of probably wraps up the 2.4 practice 4. Yeah, you bet. So what I want to just quickly show you is just a trick so you can use all the stuff we've learned with exponentials and logarithms. And you know, they're not really hard functions to deal with, especially the exponentials. But we can extend what we know to bases other than e by just, let's go back and take a little stroll down memory lane again. Let's go back to our exponentials and logarithm stuff from last year, because there's some properties that make this extension really easy to do. So for example, like what if we wanted to do something like, let's start general, and then we'll look at some specific examples. So what if we want to deal with the function a to the u? Okay, so we want to take, like, for example, the derivative with respect to x of a to the u instead of e to the u. Okay? How could we write that where that looks like an e to something instead of an a to something? Because we know how to deal with e to the u. That's easy, right? What's our standard form for that? What's the derivative with respect to x of e to the u? Right? That's easy. Okay? So can we use our properties of exponentials and logs to write that in a tricky way? What's another way of saying, can you think of a way to say a written as in terms of e? Right? Now don't make this harder than it is. You want the finished product to equal a. Right? We want to make some combination of, I'll give you a hint, a combination of an exponential and a logarithmic statement, keeping in mind that the base e log and the base e exponential are inverses, so they undo each other, right? Kirk, you got an idea?
ln a
Okay, so it's something like that, isn't it, right? We could take advantage of the fact that, we remember these two things, right? We remember that e to the base e log of a equals a, right? And the base e log of e to the a equals a, right? Because a base e exponential undoes a base e log and vice versa. Now, which one of those is probably going to be useful to us here? I'd say the top one, right? The top one. If I replace this a with, look, that's equal to a. If I replace it with that, look what we get. We get the derivative with respect to x of e to the, I get e to the natural log a to the u. But what's our property of exponents? Say if I take a power to a power, what do I do to the exponents? I multiply, right? So that's the same thing as saying the derivative of e to the log a, which is just a constant, times u, right? Now that we can deal with, right? That's just derivative of e to the hand, isn't it? So what's the derivative of e to the hand? E to the hand times the derivative of hand. Well, what's the derivative of log a, which is a constant, times u? No. The derivative of, with respect to x, right? The derivative of log a times u. What's the derivative of not log u, what's the derivative of u with respect to x? No. Like if I did, you just told me up here, the derivative of e to the u is, e to the hand is e to the hand times the derivative of hand. Well, the derivative of u with respect to x is just u prime, right? Right, that's what u prime means, is du dx, okay? So if I'm doing the derivative of log a times u, well, log a is just a constant. That just stays out front, right? So I'm going to get log a times u prime, right? Everybody see that? So there's the first link. There's the second link. Right?
Why doesn't log A get why doesn't it like get what?
Log a is a constant, right?
What is that like if it was like 4x, would it be like 4?
Yeah.
Mm-hmm. So why wouldn't that just be the
I'm not understanding your question.
like why wouldn't it so when we have the derivative of 4x we get rid of the x, right? So like
So, well, we're not done yet. We're going to be able to turn this into a simpler formula, but I want you to see this first of all, right? The derivative of log hand, or derivative of e to the hand, is e to the hand, there's hand, right, times the derivative of hand. If I gave a separate problem to you that just said, solve this, what's the derivative with respect to x of pi times u, you would just tell me pi u prime. Yeah.
So, why don't you have to derive the,
Okay, because log a is a constant, so the log of a is a constant, right? See what I'm saying? It looks like it's, kind of looks like something that wouldn't be a constant, but it is. It'd be like saying, what's the derivative of sine of pi? Derivative of sine of pi is, well, what is sine of pi? Sine of pi is 0. Derivative of 0 is 0. What's the derivative of cosine of pi? Cosine of pi is just a number, right? And so it's going to be 0 also, okay? So that's our answer, but what is this equal to? E to the log a is just a, right? So that's the same thing as saying a to the u times this answer. Well, let's put the log a, because that's a constant, let's put it out front. So there's our formula, right? So we end up with then the formula. The derivative with respect to x of a to the u is natural log of a, whatever the non-e base is, times a to the u prime. It works just like e, but if that were an e, what's the log of e equal to? 1, right? Okay. Okay, so that part's, so let's practice that a little bit. So let's try using that form. Oh, yeah. So let's try a couple practice problems. I wrote some down here. These are good ones. Let's try something like this. So what if we try... So what's y prime? Everybody, don't say it out loud. Just think about that for a second, right? So I just kind of give you a little head fake with the 11, right? That's just a constant that's not the base. So what do we do with it? What do we do with any constant that's not attached to the function? It's not part of the function. Pull it out front, right? So really all we're doing is differentiating 11 times whatever we get from that derivative, right? Well, what is that? That's just a to the u, right? Well, what's the derivative of a to the u? Okay, so we're going to get natural log 7 times a to the u times u prime, which is 1. That's our answer. Okay. No. I mean, it's a little bit harder than a base E exponential, but not much. Okay, here's another one. Okay, don't say it out loud. Let me try that. You got an answer? Daisy, you got an answer? You're trying to make this hard, aren't you?
Wait.
I was feeling a little mischievous here. This is pretty, yeah. And so it's, well, it's just pi minus 1. Yeah. Right, so this is different, right? This is not an exponential. This is just a power function. This is just x to the, could be a 3, but it's a pi, right? So we get pi times x to the pi minus 1 times the derivative of x, which is 1. Right? Okay. All right. How about, let's make it, give you a little pep. so wrap your brain around that one. We cannot take the 12 out.
So 12 is fine.
The 12 is, yeah, this is a constant that's actually a base, so it's part of the function. Okay, so what's the first, what rule applies here? What's the product? Yeah, it's a product of some stuff, right? So we gotta use product rule, so when we calculate y prime, we're gonna get, let's do, how about, we'll do first times derivative of the second, how about, right? So we're gonna get 12 to the minus x times the derivative of cosine, which is okay, plus second times the derivative of the first. Well, what's the derivative of 12 to the minus x? So we got a to the u, right? So this is u, and that's a. And we're just using all we're doing is using our standard form, right? So we're going to get natural log of a times a to the u, right? So 12 to the negative x times negative 1. The derivative of u is negative 1, so all we're going to do is just make this whole thing negative. Right? And that's it. That's all we can do. So I guess we could, what could we do this? So we'll put so this goes to the bottom, right? Everybody agree? So we end up then with, we make this one big fraction. This guy, I'll color code this here. So this guy, that's a common denominator, isn't it? On the bottom, I'm getting a 12 to the x. And my first term is just going to be negative sine x minus log 12 cosine x. We agree? Same thing as factoring out a 12 to the minus x, and then putting that common factor on the bottom where it belongs, because it's a negative exponent. Okay? All right, so what about this? Let's just go through this one. This is kind of cool. So, I forgot to put the table on. Darn it. That's going to kind of mess it up a little bit, but we'll see if I still have it. Oh, it's not there. Oh, you know what? Okay, I'm gonna skip that one because I forgot to put the table on there, and I need the table, and I don't have access to it anymore, so we'll maybe do that one later. So here's the last thing for today. Then let's look at the other. So the other thing we can do. We looked at a base e, or an exponential with a base other than e. Let's look at a log. And this is even easier with a base other than e. So if we want to do some, our goal here before we leave today, we don't have much time, is to find the derivative with respect to x of a base a log of u. And let's even do this. Let's just do a base e log of x. And then we can always extend that with the chain rule to do u pretty easily. Okay, see if you remember this, because if you remember this, this is super simple. What's the relationship we remember from pre-calc? How do we rewrite a base a exponential? No, he's not either. You're almost right. So it's the other way around. So the base a log of x we can rewrite as the log of x divided by the log of a. So the log of the base always goes on the bottom. The log of the argument goes on the top, the actual variable, right? So if we do that, this gets pretty simple, doesn't it? Natural log A is just a constant, so I can just pull that out in front of the derivative, right? So this is just equal to 1 over log A times the derivative with respect to x of log x. Well, what's that? 1 over x. Okay, so let's extend that to use the chain rule now. So if we were going to do the derivative with respect to x of log u, of the base a log of u, then we would just have log u over log a, right? Right, that's what that step would become. And what's the, that's a u, what's the derivative with respect to x of log u? Right, is u prime over u. So I'm going to get u prime over log a times u. So that's my standard form. Let's write that down. There it is. So there's the other one again. Not very different. The only difference is when that's a natural log, we'd end up with the natural log of e on the bottom just goes to 1. So all you got to do is take the regular derivative of a base e log and divide that by the log of the natural log of the base. You take your regular old log derivative and multiply by 1 over log a. Okay. All right.
Does any derivative lead to something other than the natural log?